Welcome to the notes for 2-8. This is our second lesson out of 3 on area under a curve. Today we will look at a more formalized technique for estimating the area under a curve. As you work, think about what you could do to improve the estimates you make. The problem on this slide says sketch the graph of y equals x squared and use your pencil to shade in the area under the graph over the interval from 1 to 3. Our function y equals x squared is just our parent graph. We know we have a point at 0, 0, 1, 1, 2, 4, and 3, 9. Let's just reflect those across the y-axis. Sketch in your parabola. And it's telling us that we want to find the area under this curve from the interval 1 to 3. Let's go ahead at 1 and drop in that vertical line, and at 3 drop in that vertical line. What they're asking us to find is the area of this region right here. And this is what we're going to focus on using some different methods over the next couple of slides. So first, the graph of y equals x squared is shown at right, so they're just showing half of it. The interval from 1 to 3 is the same interval we just looked at, is divided into 4 equally spaced subintervals and 4 left endpoint rectangles. So that's important information to know. Letter A, find the y values of the points where the rectangles touch the curve. Remember, to find the area of this region, we're just finding the area of each of those rectangles and adding it together. If we're trying to figure out what the heights are of each of these, right, we got to think about it here as this is where our first rectangle touches the curve. This is where the second rectangle touches, the third one, and the fourth one. Remember, it's the left side. That's why we have left endpoint rectangles. With this one, you can't really tell by looking at the graph, so we need to use the equation that's given to us. So the function states that the output is going to equal the input squared. Well, our input right here is going to be 1, so this would be the same thing as 1 squared. Our input here is 1.5, so we'll be doing 1.5 squared. The next input is 2, so this would be 2 squared. And then we have an input at 2.5. When we calculate each of those, that tells us the height of each of those rectangles. So we could say here, right, we got the first one we said was what, 1 squared is 1. We have 1.5 squared is equal to 2.25. 2 squared is equal to 4, and 2.5 squared is equal to 6.25. So those are the heights of our rectangles. Now to find the total area of the shaded region, well, each of these rectangles has a base of 1/2, right? And we could calculate that if we need to. Remember, our interval goes from 1 to 3, so we would say 3 minus 1 and then divided by the 4 would give us 2/4, which equals 1/2. That's how we know that the base of each of those is 1/2. So you could do this. You could say for your first rectangle, it's going to be 1/2 times 1 plus your second rectangle is 1/2 times 2.25 plus we have 1/2 times 4. And then the last rectangle was 6.25 in height, so 1/2 times 6.25. And you can calculate each of those and add them together if you want, or you can look at this as each of these has a common factor, right? They all have the same base. You could use a little bit of algebra, factor out that 1/2, and then say you're going to add the heights of each of the rectangles together. 1 plus 2.25 plus 4 plus 6.25. Add all those together. We've got, that makes 10.25. That'd be like 10.5, 12.5, 13.5 times 1/2. should give you 6.75 square units. So that is the area under the curve using the system that they just gave us with 4 equally spaced subintervals and left endpoint rectangles. Let's look at what happens if we change that to right endpoint rectangles. So the same setup, we still have 4 subintervals, still using the same function. Letter A says find the y values of the points where the rectangles touch the curve. So now, when we look at it, when we're looking at our first rectangle, remember, these still have the same base. They're all still 1/2. But our right endpoint rectangle gives us a point right here. Okay, so our input on this one would be 1.5. So we have 1.5 squared. For the second rectangle, it hits here. That input is 2. So this is 2 squared. The third one, we're going to go from 2.5. And we're going to square that. And then the last one, we've got this point way up here. This would be 3 squared. So notice these are a lot of the same values we just had in the previous problem. This would be 2.25. We had, the next one was 2 squared, which is equal to 4. Then we had 2.5 squared, which is equal to 6.25. And then we have 3 squared is going to equal 9. Those are the heights of each of the rectangles now. And again, we can do just like we did in the last one. Each one has a base of 1/2. And if you want to write them out, 1/2 times 2.25 plus 1/2 times 4 plus 1/2 times 6.25 plus 1/2 times 9. You can do that. I don't know why I just did that. I was telling you you can do it. Or like I said, you can also just take it and do it this other way. Factor out the 1/2 and do 2.25 plus 4 plus 6.25 plus 9. And when we add those together, let's see, 8.5, 12.5, it looks like we are going to have 21.5, and we still need to divide that by 2, which is going to give us 10.75 square units. Okay, so slightly more than the last one, right? This one was 6.75, but we know that this one was going to be less, right? Because we've got, space missing. This one, we know it's going to be a little bit more because each of our rectangles goes across our curve. So it's not just the area under the curve, there's a little bit of additional. So in our previous problems, we found that our areas were 6.75 and 10.75. What are some different ways we could find a better estimate? Well, there's a couple options that come to mind. One option we could do is we could say, we call this option number 1. Let's do that instead. Option number 1, we know that the 6.75 is a little less than our area. We know 10.75 is a little bit more, so our area has to be between those. So one thing we could do is we could always average our 6.75 and our 10.75. That should give us something that's in between, which we know our area is in between. Another option that we have is to create more subintervals, which gives us more rectangles. Okay, so we got more rectangles. It's going to help us. Okay, it is going to be more work, right? It's going to be more work for us, but it's going to be a better estimate for us as we do it too. And let me explain what I mean by that here, looking at that next slide. Here you see the same region that we've been working with is now divided into 4 and 8 subintervals using left endpoint rectangles. It asks, which graph gives a closer estimate of the exact area under the curve? Well, when we have 4 subintervals, you see there's a lot of space still open here. But when we break it into 8 subintervals, you'll see we have more little spaces, but they're all much, much smaller. So the more rectangles we can cram in there, right, the less extra space that we're going to leave under the curve. So in this case, this one will give us a better estimate, or one that's closer to the exact area of that space under the curve. So the next problem says, find the estimate for the area under the curve for y equals 4x minus x squared over the interval from x equals 0 to x equals 4 using 4 subintervals and the given method. So the given method for the first one, right, is that we're going to look at the left endpoints. So before we can do it, let's take a second here and figure out, what does this function look like? That's just going to be a parabola, right? It's going to be a parabola that opens down, and we've got that 4x. So let's factor it. Let's put it into factored form. We'll factor out our x, and we have 4 minus x left over. That means we're going to have an endpoint at 0, or not our endpoint, but I guess for our function it would be our endpoint, but it's just an x-intercept, and then we'll have one at 4. Our axis of symmetry is going to be at 2, so if you plug 2 into that function, we should get 4 as the output. And it just has standard growth, so over 1, down 1, over 1, down 1, and then we'll just sketch it in. So this is just a parabola that opens down like that. All right, so to use the left endpoints, okay, so first of all, interval goes from 0 to 4. You're going to look for your delta x. We're going to do 4 minus 0, and we're breaking it into 4 subintervals, so each one is 1. Delta x equals 1. So we've got a subinterval here, a subinterval here, we've got one here, and one here. So each of those rectangles has a base of 1. So if we're looking at writing it out, we've got 4 rectangles. If we're going to find the area, we're going to be adding all of those together. Each one has a base of 1 right now, and we'll write it in here. We're not going to factor it out right yet. When we look at the left endpoint on this one, if I wanted to start going up on my first rectangle, I would go up until I hit the function or the curve. But you notice it already hits the curve right here. So we're not even going to take it up. The height of that one is 0. So the base is 1, the height is 0. For the second one, we're going to take it up the left side till we hit our curve. That's where we hit it. So go ahead and sketch in the rest of that rectangle. So it looks like our height there is going to be 3. So we're going to do 1 times 3. For the third one, we're going to take it up the left side till we hit the curve. It looks like it's going to hit at the vertex of the parabola. And we know that vertex is up at 2, 4. So we're going to say our height is 4. And then the last one, going up the left side till we hit, and it looks like it also hits at 3, just like our second rectangle. Well, if we were taking that and calculating the area, it would be what? 0 plus 3 plus 4 plus 2, which, I'm sorry, why did I write 2? It's supposed to be 3. Sorry, little boo-boo. We caught it, right? This height was 3. This one was 4. So 3 plus 4 plus 3 should be 10. Should be 10 square units. Okay, so that one was using left endpoints. Let's do the same thing now with right endpoints. So let's sketch the parabola. It's the exact same one. Nothing's changed with it. So take it, put it there. We're still going to do 4 subintervals. So we'll do one here. We'll have one here. Then we'll have one here, and we'll have one there. Okay, so when we're doing right endpoints, right, the base is 1. When we go up the right side of this first rectangle, we're going to go up until we hit, and then we come back to the left, drawing that rectangle. So it looks like our height is 3. For the second one, the base is 1. We go all the way up till we hit it on the right side. Come back and down. That one has a height of 4. The third one, we come up, right? Base is 1, comes across. This one has a height of 3 also. And the last one, our base is 1, but you see it already touches on the right side, so its height is 0. So if we write that out here, you'll see that our first one was 1 by 3 plus 1 by 4 plus 1 by 3 plus 1 by 0. And the part I'd like for you to see here is, let's use a highlighter, right? Notice we have some similarities. Those ones appear. This one appears again in that same order between them as we're going across. Okay, now you'll see the 1 times 0 also appears in both of them there, but what I want you to see here is there are some similarities between our left and right endpoints. This part of it ends up being in the same exact order as you're going through. And we'll look at that a little bit more tomorrow, but it's important that you have that marked down. And again, I think our area on that one was also 10 square units. So there are similarities between left endpoints and right endpoints. The next slide states, find the estimate for the area under the curve y equals 2 to the power of x over the interval x equals -1 to x equals 2 using 6 sub-intervals with left endpoint rectangles. So we're talking about 6 sub-intervals with left endpoint rectangles. Let's get started with that. First thing here, just notice that on your graph, this scale on your x-axis is not going by ones. This is -1.5, this is -0.50, 0.51, 1.52, 2.5, just so you're aware. Okay, that's our x-axis. Our y-axis does go by ones. It goes up 1, 2, 3, 4, 5, and so on. Well, our function, y equals 2 to the power of x, right? We know when we put in 0, we're going to get our output of 1. When we put in 1, our output is 2. 2, the output is 4. -1, the output is 1/2. So we're just going to sketch that curve in. Looks just like that. We're asked to find the area over that interval from -1 to 2. So let's just go ahead and drop our verticals at -1 and +2. And that means we're looking at finding the area of this region right here. All right, so first thing, our delta x that we're looking for, right? We're going to do 2 minus -1, and then divided by the number of subintervals. So we have 3/6, which is 1/2. So delta x equals 1/2. And you see that actually works out nicely with this graph. And then we've got 6 subintervals. So I'm going to kind of draw them out so I can see them. There's one. I'm going to just do every other one in blue so they stand out, and I'll do the other ones in red. So hopefully they will stand out for you. If we're going to draw in our rectangles, let's do that. I've got my first one. It's a left endpoint rectangle. So start on the left side, go up to your curve, then just come back and draw it in. And you can do that with each of them. All right, just go up to your curve, then go across. There are your rectangles. We already know that each of these has a base length of 1/2, right? Each rectangle has a base length of 1/2. So just like on the previous problems, we need to figure out what the heights are going to be on that left endpoint of each of the rectangles. To do that, we're just going to use that function, y equals 2 to the power of x. Remember, these values are going to be your inputs. So we're going to start with -1, and when we plug that into the function, we have 2 to the negative first power. Then we have the second one, 2 to the negative 1/2 power. Then we have 2 to the 0 power, 2 to the 1/2 power, 2 to the first power, and then 2 to the 1.5 or 1.5 power. To calculate our area, right, you can set up the template however you wish to do it here. You could say that we've got 0.5 times 2 to the negative first power, right? We've got 6 rectangles that we're finding the areas of. So we've got negative 0.5 plus 0.5 times 2 to the power 0, plus we've got 0.5 times 2 to the 1/2 power, plus we'll put that here, and 0.5 times 2 to the first, plus 0.5 times 2 to the 1/2 power. Right, and to find our area, we just take it and we can calculate all of those together. Let's go ahead here. Let's just type that into the calculator. Right, no matter what you do there, it's going to take a little bit of typing into the calculator to get it. So let's get that out. And we'll just start typing it in. Just take your time when you're doing it. 0.5 times 2 raised to the power of negative 1, arrow over, plus 0.5 times 2 raised to the power of negative 0.5, arrow over, plus 0.5 times 2 raised to the power of 0. I guess I didn't have to put that in. I could have just calculated that, but that's fine. Don't forget your plus sign because that'll throw off your answer. Plus 0.5 times 2 raised to the 0.5 power plus 0.5 times 2 raised to the power of 1. And I think we got one more, plus 0.5 times 2 raised to the power of 1.5. Type them all in, we hit enter, and you see that the area we get is about 4.2249. Okay, so we're trying to take it 4 decimal places. And that would be square units. Now that's a lot of typing into the calculator, so if I can keep your attention here for just another moment, let's talk about how we might be able to write this one in sigma notation. I want you to look at the series that you have written there, and I really want you to focus on what part of the series is changing each time. Notice just the exponent is changing. Just the exponent is changing, and it's changing by that same amount each time. The common difference, it's adding a half each time. So if I wanted to write this in sigma notation, and this is going to help you in your homework if you're following along, okay, I know that my argument or that function rule is always going to be 0.5 times 2 raised to some power, but this is the part that's changing. So can we come up with a function or an expression to represent these values up in the exponent? Just think about the series that we have. Negative 1, we have, or just write it as a sequence, negative 0.5, 0, 0.5, 1, 1.5. If I asked you to write out the function rule, you could probably tell me that for starting, with our 0th term here, it'd be like saying negative 1 plus 0.5 times n, right? Because we're going to add 0.5 n number of times. So let's add that in up here, negative 1 plus 0.5 n. Or you could write 0.5 n minus 1. Those both mean the same thing. And so we'd be starting with the 0th term, and we'd be going all the way, right? 1, 2, 3, 4 to the 5th term, because there's 6 total. So we're going to say, let's let n equal 0, and we're going all the way to the 5th term. Now let's type that into our calculators and make sure it works. So we do alpha, window, on mine. Yours might be different. I'm going to use x's instead of n's just because it's easier to type them in. I'm going to say from 0 to 5. And I'm going to say 0.5 times in parentheses 2. If you're using an Inspire, please make sure you put the times sign between the 0.5 and the 2. I'm going to raise that 2 to the power of -1 plus 0.5x. And when we hit enter there, you see we get the exact same answer. That would probably be easier to type in versus trying to type in the big expression that we did before. So again, the answer is 4.2249 when we round to the nearest 10,000ths place. And that is it. Okay, if you have questions about the homework, please make sure you ask. I'm a little worried about a couple of the homework problems from this section because we haven't talked about them in depth. We will tomorrow on some of it, but give it your best shot. Reach out to me if you have questions.